Hello. So in continuation with our previous videos on phase transition, this is the one more video on phase transition. So here we are going to discuss the Landau theory of phase transitions. So if we go back, we have already discussed what the first order and second order phase transitions are. So here we are going to try to explain the Landau theory of second order phase transitions. But before that, we will just quickly try to understand again what do we mean by first order and second order phase transition. You might remember that Harenfest also had defined the order of the phase transition. According to him, the lowest order derivative, which is discontinuous during the phase transition, that defines what phase transition it is. So if it is a first order derivative of free energy potential, that is Gibbs free energy or Helmholtz free energy, which becomes discontinuous during the phase transition, then you have first order phase transition. If it is a second order derivative of Gibbs free energy or Helmholtz free energy, then which becomes discontinuous, then it is the second order phase transition. So first order phase transition, we have seen that there is a latent heat. So basically it requires some amount of heat during the phase transition, and that's what we call it as latent heat of either vaporization or melting, depending on the phase transition. And then we have a order parameter which increases discontinuously. I think we also discussed this order parameter in previous videos, but we will again discuss this in next slide. It increases discontinuously, so that is for first order transition. And typical example, you can say that the water to ice phase transition, or ice to water, and then vapor to water and water to vapor. So those are the typical first order phase transitions, where you know that the latent heat of vaporization and latent heat of melting is involved. If you look at the second order phase transition, there is no need of latent heat. So if you reach to a certain temperature and then suddenly this phase transition will undergo, like ferromagnetic to paramagnetic phase transition. So that kind of phase transition does not require any latent heat. That means you don't have to spend heat into or energy into these phase transitions. The order parameter here, instead of discontinuous increase in the order parameter, here it increases continuously from 0. So it is 0 before the phase transition, and then it becomes it takes some value, finite value, when the phase transition starts. For example, you have typically we can think about superconductivity. So when you cool the superconducting material, which is normally a normal conductor or insulator, let's say you bring it down to its superconducting transition temperature, and then at that temperature suddenly the material starts behaving like superconductor. There is no need to spend latent heat during this phase transition. Similarly, from ferro to para, and also for ferroelectricity, you can see. And superfluidity is similar to that of superconductivity. Instead of conductivity, here the viscosity becomes 0. So what Landau proposes, he has the view on the phase transition. It is very similar what we have seen in the previous videos. So what he says, that he suggests that the free energy of any system should obey two conditions. So free energy basically should follow these particular conditions. Free energy stands for, the Helmholtz free energy and the Gibbs free energy. So depending on what type of process you have, if your process is at constant temperature and constant pressure, then you have to use Gibbs free energy, or the free energy is defined as the Gibbs free energy. And if your process is undergoing at constant volume and constant temperature, then the free energy is called as the Helmholtz free energy. So based on that, you can use any one of them free energy to characterize the phase transition. So whatever it be, it has to satisfy the following two conditions. It has to be analytic. the free energy function should be analytic. Analytic is a mathematical term for a function which is continuous and differentiable. So if a function is continuous and differentiable, we can expand it in Taylor series. So that is why the requirement of analytic nature of the free energy. And you remember we have done this expansion of free energy using Taylor series, and then we have explained the first order and second order phase transitions already. So we will follow the similar approach here, but slightly there are some differences which we will discuss. And it has to obey the symmetry of the Hamiltonian. The Hamiltonian you might have studied in classical mechanics and quantum mechanics. So it basically has the energy and the interaction energies in that Hamiltonian. So that Hamiltonian has to be symmetric. And I think you have studied what do you mean by a symmetric Hamiltonian and all in your classical and quantum mechanics course. So when you have when you go from one point to another point, so depending on what type of symmetry we are talking about, if it is, let's say, translational symmetry, based on where you are in the solid, it should not make any difference. I mean, the sides should be surrounded by similar type of atoms, and then that's why, or you can think of in terms of interactions. So it should have all the constituents of the system should have similar interactions with the surrounding constituents. So if it is analytic function free energy, then we can of course expand it by using Taylor series expansion. In terms of this, again, the order parameter, which we will discuss. So it should be expanded in terms of order parameter. Here in this particular video, we are going to talk about Helmholtz free energy instead of Gibbs free energy. Helmholtz free energy is defined at the free energy at constant volume and constant temperature. So it depends on what type of process you are dealing with. So based on that, you have to choose whether you are using Gibbs free energy or Helmholtz free energy to characterize the process. So at phase transition, so let's talk about the order parameter here. So at phase transition, the order parameter can be defined, that is 0 above the phase transition and non-zero below the phase transition. So the order parameter will be 0 before the phase transition, and then it will take some value after the phase transition. So for example, in ferromagnetic to paramagnetic phase transition, the magnetization can be used as order parameter. So if you have magnetization, non-zero value of magnetization, then it will be para to ferro phase transition, which will be undergoing. And in paramagnetic, there will be zero magnetization because of the randomly oriented magnetic dipoles. Similarly, for ferroelectric phase transition, you will use polarization as your order parameter. So just like magnetization is because of the alignment of magnetic dipoles, similarly the polarization is due to the alignment of electric dipoles in ferroelectric materials. Similar examples can be given for like superconductivity, superconducting order parameter, just like what fraction of material starts behaving like superconducting, that you can use as order parameter. And if you have structural phase transition like cubic to tetragonal, cubic is where C and A are equal, so therefore that if C and A are equal, this becomes 0, the order parameter is 0. And when it starts becoming tetragonal, the C will not be equal to A, it will be slightly higher than A, therefore this ratio will be higher than 1, and therefore this factor, this order parameter, will be non-zero, will be higher than 0, sorry. So that can be used as order parameter. Similarly, if you have structural phase transitions, for example, again this cubic to tetragonal can also be a structural phase transition. During this phase transition, if you monitor the diffraction peaks, if you look at the diffraction peaks, that is the X-ray diffraction peaks, because structural phase transitions involve like the lattice constants changes. In this case, cubic to tetragonal, just like A, and then in cubic A and C are equal, but in tetragonal C is higher than A. So of course the lattice parameters are different, and also because lattice parameters are different, the the interplanar distance will be different. And if you remember the Bragg's law of diffraction, 2d sine theta equal to n lambda, where lambda is the wavelength, and if you keep the wavelength fixed, then if your d changes, that is the interplanar distance changes, then the theta, that means the angle of diffraction at which you see the peak, will be different, and it will be different for different type of crystal structures. Therefore, if there is a structural phase transition, diffraction peaks will show the variation, and you can use that as an order parameter. So order parameter in general, something which basically changes during the phase transition, alright, which is the characteristic of that material after the phase transition. Now let's look at the mathematical part of this Landau theory of phase transition. So Landau theory tells us that the free energy should be continuous, should be analytic function. That means we can expand this by using the Taylor series expansion. So Landau-Helmholtz free energy, typically the free energy is defined as U minus Ts, the Helmholtz free energy, where F is the free energy, Helmholtz free energy is a function of x and t. Similarly, U is a function of x and t, and the entropy is also a function of x and t, where x is an order parameter. Okay, so we discussed what order parameters are in previous slide, depending on what type of phase transition we are studying. And T is your temperature. So this, I think, typically the definition of the Helmholtz free energy. And in case of G, it will be the Gibbs free energy. G will be equal to H minus Ts, where H is the enthalpy, and you might have seen that in your experiments also, that the change in G will be basically in terms of change in enthalpy also. So sometimes it is also called as latent enthalpy of instead of latent heat, it is also called as enthalpy of phase transition. So at x is equal to x0, that is the equilibrium point, or we can say that is the phase transition point. FL is L symbol is given because of the Landau's theory, just to give him the acknowledge his contribution to the phase transition theory. So FL of x0 of at t is minimum at x is equal to x0. Okay, so you know that will be the equilibrium. Whenever there is equilibrium, there will be minimum value of the free energy. So at x is equal to x0, the equilibrium will be achieved. Since the order parameter goes to 0 at the phase transition, so actually it is 0 higher when it is higher than when it is above the phase transition, and then it starts taking value greater than 0 when after the phase transition. So you can think like this region will have higher value, will have x equal to 0, and then this region will have x equal to greater than 0, and at the phase transition you will have x equal to 0. So we can expand the free energy in terms of this order parameters just like this. So here if you see, you have this F0 which simply depends on temperature, and then you have this term which depends on temperature, and then the order parameter x. Similarly, if you look at the third term, which is 1 over 4 F4, which is again function of temperature, and then you have x, which is the order parameter. So if you look at closely here, we do not have odd terms, so that is how it is defined, this particular function. So the odd terms are supposed to be 0, and then there are again certain conditions on this F2 and F4, so we will see that. So F0, F2 and F4 are the expansion coefficients here, which depends only on temperature. Now simple power law we can assume for F0 is anyway constant, only depends on T, so doesn't have to worry about this. But if you take this F2, okay, F2 is the second order, should have it's you can say coefficient of second order term in the Taylor series expansion. So we simply assume that it is a linear function of temperature. So that means it's simply some constant is multiplied alpha t minus Tc, linear function of temperature away from the critical point. That critical point is the phase transition point. So when you go away from the phase transition, you have this you can have some value of F2, and when you are very close to the phase transition temperature, if you remember, we have done in critical exponents, so it is a similar expression in terms of critical exponents. Instead of simply to the power 1 in critical exponents, you will have some power there, okay, which will be which will be less than 1 or more than 1, depending on. So in short, this function will basically be very complicated dependent will have very complicated dependence on temperature when it is close to the phase transition temperature, and when it is away from phase transition temperature, one can assume that the dependence of this function on temperature is linear. Okay, that is the simplest thing we can assume, because it is a function of temperature. So the simplest function of temperature is the linear function that is simply some constant multiplied by the temperature. And when you reach to very close to the phase transition temperature, then this linear dependence is not valid, because there are lots of fluctuations in the density of the material during the phase transition. So the solid to liquid phase transition, for example, the density changes suddenly, okay, and then therefore the fluctuations in the density are too large to assume that it is linear dependence. So it is very close to we can say not only density, but all the parameters, all the thermodynamic quantities which depend on the density will also have this kind of complicated dependence on the temperature. But if you go slightly away from the phase transition point, you might have simpler dependence, or we can assume the simpler dependence like this linear dependence. This function changes the sign at Tc. Okay, so at Tc this function will become positive to negative, and or negative to positive, depending on what type of process it is. Whereas the alpha, which is constant here used, and F4, both are always going to be positive quantities. So these are the restrictions actually, or defined these are the conditions put on the Helmholtz free energy when it is expanded in Taylor series expansion. So if we can now simplify this, or rather we can just rearrange this by using this particular expression for F2. So we can substitute F2 is equal to alpha T minus Tc x square, and then rest is simply like that. And we also restrict this our expansion to simply only fourth order term, like a to the power x to the power 4, and we neglect the higher order terms. That is a typical way of using the Taylor series expansion, that higher order terms normally contribute very less, because the order parameter here x is going to be very small number, and it will be a fractional number, and when you take powers of them, it becomes even smaller. So let's look at what will happen at equilibrium. So at equilibrium, the FL, that is a Gibbs Helmholtz free energy, will not change as a function of x, okay, as a function of order parameter. So FL, this derivative will become therefore 0. If there is no change in FL with respect to x, the derivative of that with respect to x will be 0. So that if you substitute that in here, if you take the derivative with respect to x, this is, and say that it is 0. Now of course this is only function of temperature, so there will be no dependence of x, so this also will be 0. Here in this term it will be x square's derivative will be twice x, so you can get rid of this 2 and then the 2 multiplied to x, so you will simply have alpha T minus Tc x, and then in this case it will be 4 times x cubed, the derivative. So that again the 4 will be cancelled, and you will have simply F4 x to the power cube. So this equation gives you two solutions. One solution is this equation can be satisfied when you substitute x is equal to 0, so that is one solution, and then another solution is when x square is equal to Tc minus T alpha upon F4. Simply just take this term on the other side and then divide it by F4, you will get x cube, and then this x you can cancel, so you will get x square is equal to this, and this will be, there will be no order for Tc greater than 0. Actually it should be T greater than Tc, sorry, it should be T greater than Tc. So what do you mean by that? So if you take T greater than Tc, this term will come out to be negative, and square of the negative and then if you take the square root of x square, you will get x, that is the order parameter, and negative numbers square root will be imaginary. And you know, order parameter is a physical process, a physical phenomena like magnetization, polarization. It cannot have imaginary values, so therefore that value cannot be is not basically a physical meaning. It does not have any physical meaning, so it is not allowed mathematically. Although it is allowed physically, it has no significance. Therefore we will say that there is no order when the temperature is higher than Tc, okay, because x does not take any real value. So x is equal to 0, and then x is having this value when the temperature is lower, so this is where it will be, and this will be the x is equal to 0 point, and this x greater than 0 will be this case when T is less than Tc. Okay, so if you use this expression for the x is equal to 0 in our original expression for FL, you will see that x is equal to 0 means this term is 0, this term is 0, so you will simply have this f0. So that is what we have here. And if you substitute the other solution when x square is equal to this Tc minus T upon T times alpha upon f4, you can substitute that here. So x square is equal to Tc minus T alpha upon f4, and then you will get T minus Tc square, okay, here T minus Tc square. First term will be as it is, so square of this alpha square and then divided by f4. So that is what we have here, but with half multiplied. Now in this case it is x to the power 4, okay, so x to the power 4, that means Tc minus T square alpha square f4 square, and now f4 square and this f4 square will get cancelled, okay. So that's why you will also get similar term there, alpha square f4 T minus Tc square, okay, and when you add these two terms you will get simply 1, okay, instead of these two terms, because they are similar terms now, right. So this gives you the expressions for the order parameters and the Helmholtz free energy at equilibrium, that means at phase transition temperature. So all parameters like entropy and all are continuous. So this is the FL's behavior here. This is this equation, okay, defines the FL here, and then at this point that x is equal to 0, FL takes this particular value f0 of t, and then when it is lower it takes again this value, but it does not have any order here, so it does not have any meaning to that part. Or we can say our treatment is not valid when the temperature is higher than Tc. So this is a second order phase transition because entropy is continuous. Entropy is nothing but the first order derivative of free energy. You can see here, if you differentiate this with respect to temperature at constant volume, you will see that you will only get this entropy, okay, and then take the difference, you will only get the entropy, okay. So this is what is about the Landau theory of phase transition. So Landau theory of phase transition can explain the second order phase transition, and it basically is based on that the gives the free energy function is analytic function, and it has to be expressed like this, where the odd order terms in terms of order parameter are set to 0, and then there are certain conditions on this f2 and f4 that we have discussed, that f2 changes the sign during the phase transition and f4 is always positive. And then we use the equilibrium condition that FL does not change at equilibrium. So by using that condition we can write down the x, we can find out the values of x with different at different temperatures and at different points in this FL versus T diagram, and then we get the values of expression for FL during the phase transition and after and before phase transitions. Alright, so this is all about the Landau theory of phase transitions, and we will stop it here.